Hey there, welcome back to Farmcraft. I'm John, and recently I lost my mind and dove headfirst down the hydroelectric rabbit hole, and I've gotten way deeper in this project than I ever thought I would be. Quick summary, I installed the pipe, I 3D printed some turbines that I designed, and got pretty marginal results on the amount of power I was generating based on what this system should be able to do. So I decided to come at this more scientifically, and in the last video I started building a dynamometer which will allow me to measure the power output of the turbines directly. If you haven't seen that yet, you're probably going to want to watch that for this video to make sense. At the end of the video I thought I was pretty much there, I just had a little more work to do, but it turns out there was a lot more challenges in store for me on getting this dyno right. So that's what we're covering in this video. It's pretty interesting. There's a fair amount of machining, precision challenges, engineering and design challenges. Let's just say this dyno has pushed me to my limits in several different ways. Let's get into it. So yeah, this thing was wobbling around, partially because it has play in the shaft, and a lot of people had some really good ideas. They said, why don't you take a nut and turn one face of it so it's a cone, so that when it screws against this bearing it will center it. And that's not a bad idea. The problem is the threads are really not running true. The bar is slightly bent where I threaded it. So even if I did get this fixed so that the play was gone, it's still not going to run true. So I got to fix that. And some other people had some ideas, you know, why don't you put epoxy on the threads and then turn that down? Well, then I wouldn't be able to thread a nut past it and lock everything into position. There's a lot of ways to skin this cat. I decided it would be easier just to get a new shaft and do it right. This guy was threaded to lock it to the shaft, so I'm going to have to change that. I think what I'm going to need to do is have a way to tighten a set screw and put a little flat on the shaft for the set screw to go against. This thing is shimmed because the shaft was bent and this was offsetting that, but new shaft and a new way to attach it. I think the shims are no longer going to be valid. So here's the plan. This is the old shaft, and that part was turned down there for the bearing, and then I threaded the rest of it. The new shaft, I'm going to turn this entire area down for the bearing. That will accommodate the actual support bearing here, and then also this bearing, which is the same bearing, further up the shaft. This part needs to be in between and driven by the shaft. Rather than this short section here of 12 millimeter, we're going to have, great mixing units, we're going to have 2.3 inches of 12 millimeter, and then I'm going to thread the rest. That should work much better. First I need a center drilled into the end. I'm using a 4-jaw and I'm going for maximum precision here. That's within about 4/10, I would say. Pretty darn good. $491. I need 471. So I've got 479 and a half. Do I have any taper on this thing? That's 479. And that's 479. So yeah, it's deflecting a tiny bit in the center. I mean, it's actually more like 3/10. 479 and a half. I really want 471. I dial in 8, I should get 1.5, and then I can polish from there. Bearing might go on there. It just might. Oh wow. Well, there's no play. It's a little looser than I expected. That's weird. There's no play on that one either. When you start trying to machine to the 1,000th, it gets to be a bit of an art. The previous shaft that I did, the bearing fit well on, and it measured 470. The inside of the bearing measures 472. So I had 2/1000ths of clearance. I figured I'd go for 471, and I got it. This is actually a little over 471, but the bearing seems to go on easier. I don't know, that's the way it is. Might be surface finish, I guess. Maybe I got a smoother finish on this one so that it slides on easier, but certainly it's going to work. Just annoys me when I don't nail it like I want. Okay, so now we need to thread 1.5 inches. There's my die, and then I'm using the tailstock to keep it centered. That should be a perfect start. There's some burrs there. I'm just using some emery cloth to get rid of them. Still tight. There it is. Okay, that part of the shaft is done. This goes here. This bearing goes like this. And it sits up against that shoulder. This guy screws on there. And the next thing that needs to happen is this. Now this had a nut screwed down on it. Spaces this out away the right amount. So I think what I'm going to do is weld this nut on and then put this back on the lathe and turn the nut down, drill it out so that it fits over that 12 millimeters. That should be running extremely true, and that means our brake rotor should now have no wobble to it. Then I will drill through and we'll put a set screw in it. I'll put a little flat on the shaft where it needs to be so that this can lock down. Turbine drives the shaft drives the brake, and then we get our readings. Yeah, you get the point. So I'm going to clean most of the zinc off of this thing. And now I'm going to take the old shaft and use it as a guide for welding this nut on. I changed over to the 3-jaw. That'll get it pretty close to center. And it actually doesn't have to be perfectly centered that way. Alright, this is a little tricky actually. So it's not on center now, no surprise, I just welded that on there, but you can see it's close. Here, let me put the center there so that you can see it moving relative to the center. It's wobbling back and forth. You can make a hole perfectly true with a boring bar. Well, this is my smallest one, and it won't fit. But it'll fit in there part way. It's just once it gets out to this point here, it's not going to fit. Now, I could grind that off, but that makes the boring bar weaker. I don't really want to do that. But I'm really close. It measures about 400 thousandths in there. And this should be able to fit in like 420, 430. So what I'm going to do is bore as deep as I can to 420 thousandths, which is the width of this bit. And then that will allow the bit to stay on center as it drills. Basically, I'm making like a guide area. Because if I try to drill this now, this bit is going to wobble around and just follow the inaccurate center that this thing has, if that makes any sense. Still wobbled a little bit, but not like it would have. Yes, okay. $455, and I want the bearings 472. This should be 65. Yeah, that's always disconcerting when you dial in 10 and it only takes 4. Really? I dialed in 2 there, and it took 4. 462. Part of that was spring pass, part of it was the 2 I dialed in. I'm dialing in 4. And 466. It took 4. I guess I'll do 4 more. I really don't want to overshoot. 69. Alright, I'm going to dial in 2. Well, 72. That's what I wanted. That's the same size as the bearing. So that should go on there. Now before I take it off the lathe, I have other turning to do, but I'm going to get the tailstock out of the way and actually check it where it is, just to see. See, it won't go. Interesting. Alright, getting a little too anal probably, but I'm just going to skim it as lightly as I possibly can. That did basically nothing. I really need a way to check this. I can't have my boring bar in place and check it. Ah, I can come in from the other side of the lathe. Still no go. So if you're wondering, you can make like a wooden mandrel with a split in it that you can wedge open and make it a little bit bigger. See, now I'm measuring 473. That should go in there. Yeah, you have like a mandrel with a cut through the center, and you can put a wedge in there to make it widen. And you can then put like buffing compound on it and spin it in there. That's basically the way you would polish it to a final dimension like you do on an OD with an ID. I guess you could say I'm being lazy, but I think that's a little too anal for this. You can kill yourself with precision, there's no doubt. That's crazy that won't go. I mean, it's so close, but it won't go. So I got stuck a little bit. I'm not even going to dial anything in. I'm just going to do that same cut again. So close. I think part of the issue is that I still have the remnants of threads in there, so it's not like a nice smooth surface. Surface finish matters. I am going to try this chainsaw file. I mean, all right. I just dialed in 1. Living on the edge. it's got to fit now. There it is. Yeah. Still a tight spot on that shaft. That's going to work. Okay. All right. We are through. That was rather boring. So now I have a little issue. This face is a machined face and it's good, and that is parallel or perpendicular to the bore. But this face I had cleaned up on the belt grinder. You can probably see there I even went a little deep on that spot. So that is not perfectly parallel with this face. And it didn't matter before because it was the threads and this face that the disc attached to. But now I'm going to be attaching it to this side, so I need this face to be a true machined face. And at first it seemed like this was going to be really hard to do, but I think this will actually work. I just need to do very light cuts. See, I can't grab this because it's curved. But if I just press it against the chuck jaws and use a live center in the tailstock, I just need to plane this face to be parallel to the one on the opposite side. And I think there will be enough friction there that I should be able to do some cuts on that with a good sharp tool, of course. The very center actually doesn't even matter, it's just the outside here, because that's where the disc is going to contact. Good. Set screw, when it contacts the shaft, is sticking out just a little too far. It was rubbing on this, so don't want that. But it also marked the shaft where it needs to have a flat, so that's good. Easy solution on the set screw. Turns out my assortment has a shorter one. Yeah, see, it's starting to come through there, and it's, yeah, so it's got full thread engagement even though it's shorter. That's perfect. There it is. Oh, that's great. Now we can start putting this guy back on here. So I had several people that know bikes contact me and tell me you don't really expect these discs to be flat. And they often bend them, just give them a little bend to make them flat. Let's get a dial indicator out here and check some run out, kind of see where we are. First thing I want to check is the shaft, because that's what she said. 3/1000. Now that's all the way out here, so in theory it's less on that brake disc. And I wish it was perfect, but you know what? Nothing's perfect. So 3/1000 of run out on the shaft. Now I should mention it is possible to straighten a shaft, and someone who knew what they were doing with my equipment could probably get it running to within 1/1000th, maybe even better. But I have just not had good luck with that in the past. I mean, I can straighten them somewhat, but 3/1000 of an inch is a tiny, tiny amount. And I really think me trying to straighten that is just going to end up making it worse. That is about 1/1000 on the inner part of that hub. So that brings us to the big question, is what is it going to be out here. Got a set of wider various tip profiles for this so that I can put a wide one on there and not catch those holes as they go by. So 15 thousandths I'm still seeing. I think I'm just going to bend the disc. I mean, if I get it within a few thou, 5 thou, I mean, that's got to be good enough. First, let's go ahead and put this flat on the shaft for the set screw to lock into. Okay, get somewhere. When I do the final assembly, I'll put a little bit of blue Loctite on that set screw. Ready for this guy, with the exception of a spacer in between the two. So the spacer I was using was that width. So we've got 390. Basically, I just need to make a spacer. So I'm going to crank something like that on the lathe and we'll be back. Spacer. And then this guy. Alright. A washer. And a nut. Okay. Now we can mount the caliper. Let's see how this thing's going to do. Got it close, and I've got it marked on the end here so that I can see. But from here to right there, it doesn't touch at all. And then it is, I mean, there's really not much resistance, but there's just a little bit there. So I'm going to try to bend it. I guess the way to do this would be to bend it where it's kind of, I have no idea how hard to bend it. I'm just going to take it slow. I have a feeling if I overdo it, I will regret it. These bike guys know what they're talking about. This actually works. Who'd have thought? Check it out. That's what I'm talking about. Now, how much wobble do we get? It's not perfect like I was hoping, but it is definitely better than it was before. Still some, but I think it's tolerable. All right, I'm fiddling, trying to get this thing better, and I've got the disc. So starting here, we're at 48 thousandths. Gets to 51 at one point. So I'm within 3 thousandths of run out on the entire disc. And if that's not good enough, well, I don't know what to say. Yeah, so the disc is no longer the problem. Now I need to get the caliper to run true as far as grabbing the disc, which I think means making the caliper float. So I've been sitting here fiddling for quite a while. I've loosened these two bolts, squeeze the brake, tighten the bolts back down, try to get it in the right spot. It still wobbles, and I've done very fine adjustments on those bolts trying to get it to not wobble. I've loosened both of these so that the caliper can float, and I've also unconstrained the top here, so if this thing needs to go back and forth, that's not stopping it. Basically, no matter how I do this, this thing continues to want to wobble. Even with no braking on, I think you can probably see the vibration that's occurring. But as soon as you start braking, even though this thing's able to kind of pivot and float and find where it wants to be, it really wobbles. Now, part of that might be I'm driving it with a drill out here on the shaft, and I'm forcing it to wobble because of that. That threads are never perfect in the center. So maybe when it's being driven off of the turbine and it's just the turbine and the disc brake, maybe it'll work. I suspect that really I have a design flaw here because I've got a caliper grabbing this spinning disc, and then I also have a bearing on the shaft. The disc is mounted to the shaft, so I have a triangle there. And if anything is not perfect, it's going to show up, right? I think if the lever was mounted somewhere else, not on this shaft, and I could get it stable, then I just have one contact point, and that's between the caliper and the disc. But here I've got this triangle going on, and I think I'm too constrained. So no matter what I do, I cannot get it perfect. I'm not sure on that, but that's my thinking at this point. So we have a mouse problem, mostly in the chicken coop out there. So Jennifer and I talked about it, and she decided to go to the pound and see if we couldn't pick up a cat that can live mostly in the chicken coop and outside and handle the mice. This is what she brought home. Yep, that's a cat with her 2 kittens that are still on milk. Why get 1 cat when you can get 3? Hello. Ooh, you're ferocious. I just spent the better part of a day redesigning this thing, and I've got it pretty good. So rather than pivoting on the central axis, which I can even see it wobbling a little bit, it's pivoting over here. And I can't show you much of that pivot because if it pivots too much, it lifts the brake caliper right off of the disc. And if it pivots that way too much, the back of the brake caliper hits the edge of the disc. So it kind of has to be held right in that position. But it is free to pivot and load up the load cell. This is the stop that's preventing it from going back and hitting the brake. You can see there's a tiny bit of rub there, and I may work on that at some point, but it's pretty darn good. Put a U-joint on the drill so that when I drive it, at least the drill doesn't shake quite as much. But that shaft wobbling is definitely still causing some wobble, but you'll notice on the previous version when I was on that shaft, I had a lot of wobble in this lever out here going to the load cell. And now, even though there's still a little bit when I really start loading it up, it is greatly improved. So a lot of that is coming from me driving this with a drill, I think. Remember, this is going to be being driven from the other side of the shaft. There's not going to be a mass of a drill sitting here shaking around. Everything should be running more concentric when it's actually in use. But I think this version is a definite improvement. I'm getting a lot less wobble. I took time to make sure everything was real precise when I did this. Yeah, let me show it to you real quick. To give you the basic gist, I did the lever. I welded on a piece of solid bar. That actually was. It wasn't a pipe. And then went ahead and did all of this, getting it exactly where it needed to be so that I could mount the caliper to it. Then I took it to the mill, and in one setup, I milled that face so that that was nice and flat, and I drilled the hole so that the hole for the pivot was perfectly perpendicular to the face that was going to be mounting the caliper. Then I figured out what the spacing needed to be, and I turned a pin here to space it off of this plate. There's a bolt there holding that pin on. And then I reamed it to a 1/2 inch hole, and then I turned a 1/2 inch pin, and those fit together perfectly. Put a little bit of grease in there, and that's good. I'm real happy with that. Then I got the caliper where I wanted it on the disc, and lined up where it needed to be with this plate, I clamped it, took it off, and punched the holes, drilled them, mounted the caliper. And then I got this in the comments. You definitely need to loosen these. I didn't really realize what these were for. These are kind of your fine adjust of that caliper position. These things have a slot in there so that they can each move side to side. So you loosen that, you squeeze the brake on the caliper so that it lines up to where it wants to be, and then you tighten those down. And I did that. It still wasn't perfect. I did a little bit of fine adjusting manually and got it pretty darn good. I put the stop in. I just hooked this. That's temporary, I guess. Don't worry, it's only temporary. That's probably permanent, isn't it? It works just fine. The load cell's under tension. This stops it from hitting the brake. I need to put the ripometer back on. There you go. Dyno version 2000. Still not perfect. It's as good as I'm getting it, and I think it will certainly work. It's definitely better. What do you think? Alright, so now we need to calibrate this thing, and figuring out what that lever arm is pretty darn difficult with it in this situation, because I can't measure from the center of the shaft. How do you do that? Well, we're just going to trick it. So I've got a breaker bar, and I can apply torque to it. You can actually see the reading changing here, the blue line. So I'm going to apply a known torque to that. I'm going to tell it the lever arm is 1 foot. I will just basically back calculate, well, how many pounds would that be if the lever arm was 1 foot? So basically I need to figure out how many foot-pounds am I putting on here. And I weighed this guy out. It weighs 12.699 pounds with the string that I will be putting right there. So I need to measure from the center axis, which would be the center of that pin right there, to right there. Yeah, that's 16 1/8. On the money. 16.125 inches. Now, right now, it says it's got 14 foot-pounds of torque on it. So we need to change that. Tare. Proceed. So this is telling it this is 0. There's no torque on it right now. I should mention that the brake is locked right now. That's why the shaft isn't just rotating down. Proceed. Accept. Proceed. Okay. Brace is right there. Okay. Still showing 0.1. We're going to call that close enough. We're going to try this here. Let me set the lever length. And we're going to set it to 1. 1 foot. So, that length I measured is 16.125 inches divided by 12 inches is that many feet. And then I'm going to multiply that by the weight, which is 12.699 pounds. So foot-pounds gives us 17.064. As far as the system is concerned, that's how much weight the load cell is seeing. Now obviously the length of the lever matters, but we're kind of bypassing that because we're actually doing known foot-pounds. I need to tell it that this is 17 foot-pounds. So, calibrate. Tare first. We already tared. Enter test weight in decimal pounds. 17.064. Let's put the weight on there. So the instructions at this point say to hang the test weight, and now it is taking multiple readings and averaging them to figure out exactly how much force is on the load cell. Just notice that thing's swinging slightly, but I suspect I'll be doing this again, so we'll see what it comes up with. We should be close. 17.1 foot-pounds. 17.06. That's a correct roundup. Given its intents, that's right on the money. Sweet. Now I'm going to check something. Now you can see the torque readout right now is negative 0.5, and that's because I took the breaker bar off. I should have re-tared it here, but that doesn't really change what you're about to see. But we're going to put a torque wrench on it and hit it with 20 foot-pounds and see where it peaks. It only said 16. And you have the problem of, is the torque wrench accurate? Let me get something that's right at the low end of this torque wrench. Let me get the smaller wrench out. So that's 120 inch-pounds, which is 10 foot-pounds. Are my torque wrenches really off that much? I've checked them before and they were pretty accurate. The reason I can't go too high is because if I crank on that, those nuts are jammed together. But if I twist left too hard, and that's the way this whole thing's designed to work, because that's how the turbines are going to be spinning, that nut will come off and I can't get a reading. But this thing is consistently giving me 4 pounds low. So let's see here. Here's 20 foot-pounds. Well, that only went to 14. 14 and a half. Okay, that was a little more than 4. But that's right at the lower end of the scale for this torque wrench. So here's 25. It's making a liar of me. 19. Here's 28. 22. Now I'm consistently getting 6 low. Strange. So here's 30. So let's see if we get 24 again. 25. 32. 26.6. 34. Just under 29. Really not sure what to make of that. Let's try this guy again. So we know this is 17. Now it's giving me 14. That's really strange. Alright, who out there is the genius that took one look at this and said that won't work? Because this won't work. So I'm taking you through my thinking throughout this whole process. Basically, there's a design flaw here, and there is a solution. So if you're interested in trying to figure out a little engineering challenge, pause the video, think what is the problem, and then think, how do I solve it? It took me a little while to get there. I like the idea of this design because it gets this off of the shaft, but there's a problem here. When this thing pivots, it's not pivoting in the same circle that this pivots. What that means is, when you lock the brake, this thing can't pivot anymore, and it can't load up the load cell. The only thing loading the load cell right now is the flex of that. It's not actually the torque that I'm applying. So like I can pivot this thing to the stop, lock the brake, and now it doesn't hardly load the load cell at all. I can pivot it all the way and pull really hard on it, lock the brake, and it will stay there. So there's no way to calibrate this thing. You know, it might actually be reasonably accurate when you're partial brake and the thing is still spinning, but how are you going to calibrate it? In order to calibrate it, you have to find a 0 and then lock the brake so that it doesn't spin, tear everything. Yeah, I don't know. I don't think that's going to work. See, with the other one, because it's on the same axis of rotation, if you lock the brake, the caliper will just move with the disc, but it'll still spin.
A few moments later.
All right, I called the engineer who built all this, and he helped me through this. I think this is going to work, actually. One thing is, rather than using the brake to do the calibration, because the calibration has to be static, the system is stopped, and I was locking the brake to do that, but the brake won't allow this thing to pivot anymore, is we just put this pin in here. So that allows this to pivot and adequately load up the load cell for the calibration. Simple solution there. And I got it calibrated, and it's given me really good answers now. Very consistent. I also put this in more of a, it's not a rigid mounting. These bolts they're just through one layer of sheet metal, and the hole's a little big, so they're welcome to like rotate and pivot however they need to. So that load cell's not being side loaded there, but it just keeps it from like sagging down and up. The way I had it was not giving me consistent results. The other thing, which was a real good suggestion from the engineer, is my threaded rod stop, we also put a preload spring on. So this spring is under compression. I tightened down this nut and then jam nutted it on. So that is holding it out. So there's really no movement on it, but the only way it can move is that way, and that puts additional load on the load cell. I also moved the load cell down because that puts us more in the range of what the load cell is capable of. Basically, it shortened the length of this lever so that it puts more force on the load cell. So let me show you some things here. So you take a look at this display here. The tare, let me clear everything. The tare says negative 0.1 foot-pounds. It'll wander a little bit after you tare it, but negative 0.1 foot-pounds I'm not worried about. So I'm going to put some torque on this with the torque wrench. And I've got it set to, what am I going to set it to? Let's set it to 20 foot-pounds and see what we get. That'll give us our real-time torque, and then the one above it will give us our peak torque. Click. 20.3. Okay. Let's go to, that's the wrong way. Let's go to 25. Click. 25 on the money. Let's go to 30. 30.2. And let's go to 35. 34.5. Ah, off by half a foot-pound. I'm just kidding. That's awesome. This thing is definitely calibrated, but that is with the pin. That's not with me using the brake. See, I would have the same problem right now if I lock the brake. So the brake is locked, and I'm still on 30 foot-pounds. Let's clear our peak there. I get 24.7. And that's because the brake is kind of fighting allowing the rotation that's needed to adequately load up the load cell. But that's only an issue when the brake is fully locked. When I'm using this thing, I'm going to be slowly increasing the brake pressure, and the brake is going to be sliding. Yeah, when that thing is under sliding friction, the movement is going to be able to go whichever way it needs to go, and we're going to get an accurate result. I'm quite certain of that, but let me prove it. So breaker bar. Alright, so what I'm going to do, let gravity bring that thing down to 90, and then I'm going to lock the brake. This is tough to do because there's not a lot of weight there. It's very sensitive. That was a little rough. Let me try that again. Still a little rough, but I'm getting the same reading, so let's go with it. Alright, I'm going to tare it right there. So because I kind of came at that dynamically, the brake and the load cell, that triangle that's not allowing it to pivot wasn't a factor there because it slid into position, if that makes sense. There should be nothing fighting the load cell right now as far as its position. What I'm going to do is the same thing with this weight on here. 12.7 pound weight. And this is 16 1/8 inches out. That equates to just over 17 foot-pounds, like 17.1. So I am going to attempt to do the same thing using the brake, letting it slide into position. Yeah, that was a bit of a shock load. So yeah, I ended up with 21 foot-pounds because it went too fast. That was a little better, but I went too far, so I'm getting a low. Still a little bit of a shock load, and I got 18, so just over what it should be. I think you get the point. I think this thing's going to work. It is giving me accurate readings while it's sliding, I think. So one more thing I added here, I threaded the end of the pin that's going through the bar. I put a Teflon washer there and then a bolt. That won't allow, it'll allow it to pivot, but it won't allow it to shift side to side at all because obviously the caliper's mounted to that and that would adjust how it breaks. I also installed a new connector on this so that that's all nice and buttoned up. It was missing a proper connector when he sent it to me just because the connector wasn't available, but I've received it and installed it. The dyno is actually done and ready to use. So now we can finally get on with the turbine. And we're going to do that in the next video. I really thought I was in this video going to finish the dynamometer and go on to the turbine all in one video. But this ended up being way more time consuming and way more work than I was expecting. It seems to be a theme on this channel, I don't know. But anyway, we're going to do that in the next video. Thanks for watching. We'll see you then.